Hi guys, sorry about that glitch with the video. Okay, so let's look at this again. Digits from 0 to 7, making a 4-digit number. Repetition is not allowed. So am I to presume that this should be 8? 1, 2, 3, 4, 5, 6, 7, 8. And then presume if one of the digits gets chosen that I'll have 7 choices left, and 6 choices left, and 5 choices left? I guess so, but let me just tell you, no, we're wrong. And where things are wrong is with that first value right there. Let me ask you, if I write 1, 3, 5, 2, or sorry, if I write 0, 3, 5, 2, is that considered a 4-digit number? What about this? 3052. Is that considered a 3-digit number or a 4-digit number? The second one is, the first one isn't. So what that's saying to me is that if I'm looking for a 4-digit number, that first digit cannot be 0. It cannot be 0. Because if it is, then it's not considered a 4-digit number. So that being the case, if the first digit can't be 0, that makes 7 choices available. 1, 2, 3, 4, 5, 6, 7. Let's pretend a 2 ended up in the first position. That leaves me with 1, 2, 3, 4, 5, 6, 7 choices available. 1, 2, 3, 4, 5, 6 for the next position. 1, 2, 3, 4, 5 for the next position. For a final answer of 1470. What about if I said repetition is allowed? Well, I know that the first digit can't be 0. So 7 choices. But the second digit can certainly be 0. So that's going to leave me with 8. Repetition allowed means that I'm throwing the block back in the bag. 8. Repetition allowed means I'm throwing the block back in the bag. 8. 3,584. Okay, what if we look at the number has to be less than 4,000 and repetition is allowed? Less than 4,000. Well, anything that starts with a 1 is less than 4,000. Anything that starts with a 2 is less than 4,000. And anything that starts with a 3 is less than 4,000. So it can't be 0, but it can be 1 or 2 or 3. So I've got 3 choices available for the first position. Repetition is allowed means that I look at the block and throw it back in the bag. 8 choices. Look at the block, throw it back in the bag. 8 choices again. Look at the block, throw it back in the bag. 8 choices. Final answer of 1536. Okay. D says, what if the 4-digit number is even and repetition is allowed? Well, let me ask you, if I gave you the number 252, would you say that that number's even? Yes. What if I gave you the number 257? Would you say that that number's even? No, you would say it's odd. What digit addresses even versus odd? Is that last digit. Tells us whether something's even versus odd. So this is going to be an important position, and we know that this can't be 0. So let's start with the first position. If it can't be 0, how many choices do I have available? 7. Let's move to the even. what are my choices for even? 0, 2, 4, and 6. 4 choices with repetition being allowed, because whatever I had here, this could have ended up as a 2, but repetition is allowed. And then when I look to the middle numbers, if repetition is allowed, that means that I've got 8 choices and 8 choices for a final value of 1792. So take note that example 8 is slightly a little bit more difficult than example 7 because of the 0 being thrown in. Let's take a look at example number 9 right now and see how we can make it even a little bit more difficult. Give me a sec. Okay, so how many 3-digit numbers can be formed using the digits 0 through 5? Well, I think the first thing that I can immediately do is that this first digit can't be 0, can't be 0, can't be 0. We know that. For it to be a 3-digit number, 0, 2, 3 is not a 3-digit number. 203 is a 3-digit number, though. Okay, so let's look for a 3-digit number where there are no restrictions. And the words no restrictions usually imply repetition is allowed. That's always something that you want to clarify if you're not certain in the instructions. But in most cases, no restrictions means repetition is allowed. Okay, well, if 0 can't be counted, how many choices do I have available for the first position? Now all of a sudden the 0 gets thrown back in the bag. How many choices do I have for the second position? I look at the block as it comes out, but because repetition is allowed, I throw it back in. 6 choices for a final answer of 180. What if I said to you, okay, same question, repetition is not allowed. So can't have 0. How many choices do I have available? Let's pretend that it happened to be a 1 that was pulled out. That means that the 1 is sitting on my desk. How many choices do I have available? 5. Let's say the second pull was a 2. How many choices do I have available? 4 for a final answer of 100. What if the number is odd and repetition is not allowed? What if the number is odd and repetition is not allowed? So we're going to put odd here. And let's just deal with our options of odd numbers, 1, 3, and 5. So hold on. If the number is odd, and it could be a 1, a 3, or a 5, that means that there's 3 choices. Let's pretend that the 1 is gone because repetition is not allowed. How many choices does that leave you for the first position? Well, I can't use 0 because that's not allowed, so that's going to leave me with 4 choices. The 2, the 3, the 4, or the 5. Okay, now if one of the odd digits is gone and another digit is gone, so an odd digit is gone and another digit is gone, how many choices does that leave me for the next position? 4. 1, 2, 3, 4 for a beautiful answer of 48. Okay, here comes the zinger. I want you to put a star beside it. It's definitely considered an application question. Please and thanks. All right, the number is divisible by 5, and repetition is not allowed. The number is divisible by 5. So hold on. Let's think about this for a second. What numbers are divisible by 5? Anything that ends in a 0 or anything that ends in a 5. Okay, anything that ends in a 0 or anything that ends in a 5. That 0, though, that's got a special case for the first digit. It can't be 0. So because of that, because we're looking for 0 having an importance here and 0 having importance here with no repetition, this is what we call a case scenario, a case 1 and a case 2 scenario. The first case that we're going to look at is that the number that we're looking at absolutely ends in a 0. Okay, that means that we're putting the 0 right there. We're putting it in. Okay, so if the 0 is gone, how many choices do you have for the first position? Take it out, display it on your desk. How many choices for the second position? And if the 0 is sitting there, right? If the 0 is sitting in that position, if the 0 is sitting there, that means that there's only one way that that could happen. The second case is that the number that we're looking for, the 3-digit number, ends in the 5. So if the 5 is sitting in the end position, and we know that this can't be 0, that means that there's 4 choices for the first position. So the 5's gone and another number's gone, and 4 choices for the next position for a value of 16. Now, because this is a case 1 and a case 2, we're going to take the 20 and the 16 and add it up, and we're going to get that there are 36 different ways to come up with 3-digit numbers that are divisible by 5. 20 of them are divisible by 0. 16 of them are divisible by 5, where repetition isn't allowed. Very, very important type of question. It's an application. Very important question. Okay. So now that we've looked at digits question, let's kind of jump back into factorial types of questions. Okay? Take a look at this notation. Let me read it to you. 7 times the permutation of n choose 3. 6 times the permutation of n plus 1 choose 3. Now, what we need to recall in order to do this particular question is our beautiful permutation formula that we looked at previously in part 1. And the formula says n factorial over n minus r factorial. So we derived that formula, we got that formula in part 1, and now we're actually going to use it. So let me help you out. let's take a big set of equals and put them in the middle of our page. And we're going to deal exclusively with the left-hand side. 7 times the permutation of n choose 3. So our formula says n factorial, that's the n, over n minus r factorial. So our n is n, our r is 3, n factorial over n minus 3 factorial. Going to do the same thing on the right-hand side. 6 times our n plus 1 is our n, and our 3 is our r. So n factorial all over n minus r factorial. Okay, let's do a little bit of cleanup. Nothing to really clean up on the left, but on the right, positive 1 minus 3. Now, this should look relatively familiar because this is factorial notation again. So hold on, I'm going to have 7 out in front. And then when I look at this factorial and I look at simplifying it, I should know at this point, based on my knowledge of simplifying factorials, that at anywhere past n minus 3, I'm going to be able to cancel. So it's going to be n minus 1, and n minus 2 remaining, because anything after n minus 3 and n after it is all going to be canceled. Same thing on the right, 6. And I know if I expanded this out, anything after n minus 2 is all going to be canceled. So I'm going to have n plus 1, n minus 1. I don't need to write down n minus 2 because that's going to be matchy-matchy with the denominator and cancel itself out. Okay, so at least I've gotten rid of the factorials. But now, if I were to expand both the left and the right-hand side, I would end up with a cubic. N times n times n would give me a cubic. N times n times n would give me a cubic. And I know from my factorial work that I'm not allowed to expand anything larger than a quadratic. So let's take a look on the left. Put your eyes on the equals. Take a look at the left, take a look at the right, and see if you see anything that's matchy-matchy. I do. I see this. And guess what? I also see this. So I can cancel both the green and the pink and be left with that nice clean expression. I'm going to rainbow. I'm going to rainbow. I'm going to put letters on one side and numbers on the other. And I'm going to get one beautiful solution, n equals 20. Hope this is helpful for when you're doing your work. Take care.